In this video, I'm basically going to repeat the famous dropping experiment, so the kinetic energy experiment done by Émilie de Châtelet. So I have this weight, which is 100 grams, as you can see. I'm going to suspend it on that bar over there. And first I'm going to let it drop from 90.5 centimeters to be precise. And then I'm going to drop it 4 times higher, so twice the velocity at 78 centimeters. And then we will see how much the displacement is. So I have already done it, as you can see. So I'm doing this at the end of the experiment. So it's a cylindrical shaped object. Okay, so in order to calculate the volume, we will have to use the equation, the formula to calculate the volume of a cylinder. Because it's cylindrical, it has a cylindrical shape. Also, I'm not using clay as she did. I'm using floral foam. I think this is an excellent material to measure impact. Okay, so here we have the results. This is the impact for the one mass going one velocity, so dropped from 90.5 centimeters. The one mass dropped from 78 centimeters, 4 times higher, so twice the velocity of this guy over here. So it's basically cylindric in shape. Let's measure the depth. Let's see. This is rather small. I think it's 3 millimeter. I think it's 3 millimeter. So now, of course, it's not perfectly even everywhere. So let's do another side. Again, I think it's 3 millimeter. And I try to let me try to position it 3 millimeters. So this one is 3 millimeters. This one, let's see. So it's more than 1 centimeter, which seems to be 1.3. You can see it, right? 1.3. Other side. The same. 1.3, a little bit less even, I guess. 1.3 perfectly, I think. 1.3. Another side. Oh, that's difficult. I think also 1.3. So we have 0.3 centimeters versus 1.3. So the depth in itself, 0.3 centimeters times 4 is 1.2, and it's 1.3, so it's 1 millimeter deeper than 4 times the depth. Okay, so if you want to calculate the volume, then we need to use this formula, which is a radius squared times pi times the height. And so for the one mass going one velocity, so the radius, well, let me show you. the diameter is 2.6, so divided by 2 is 1.3. The radius is 1.3. So 1.3 squared times pi times the depth, 0.3 centimeters, that equals 1.59. So that should be centimeter cubed. And then twice the velocity from 4 times the height. 1.3 centimeters squared times pi times 1.3 was the depth, was the height. That equals 6.89 centimeters squared. So now, well, if we normally, according to conventional science, twice, if the same mass going twice the velocity should create 4 times the penetration, 4 times the displacement. So 1.59 times 4 equals 6.36, and my result is 6.89. So we are still within a range of 6. And if we divide 6.89 with 1.59 with my results, that equals 4.3. So with my results here, this is 4.3 times more displacement as this one. So I would say pretty close to 4 times the displacement. It's, I think, an acceptable error range. All right, so let's measure it. Let's measure this side. As you can see, 3 millimeter. And then the other side, 3, I think, maybe between 3 and 4. Then the other, let's pick this side. Between 3 and 4. Other side, I think the same, between 3 and 4. Best. Now this one. .4. Other side. What's that? Between 1.3 and 1.4 to be precise. Is that 1.3, 1.4 again, between 1.3 and 4. That's difficult to see. Hold on. Alright, let's try again. What's that? Between 1.3. Yep. So once again, I tried to measure the depth as best as I possibly could. So now it seems that we have 0.35 centimeters for the 1 mass 1 velocity, and for the 1 mass 2 velocity around 1.35 or 1.3, still the same. So if we do if we take 1.35 divided by 0.35, we have 3.8. If it is still 1.3, then we have 1.3 divided by 1.3 divided by 0.35, then we have 3.7. So 3.8, 3.7, 4.3, all these numbers are hovering around the number 4. So it won't be much further. It won't, this is like the maximum deviations that we will get. But still, it's within the vicinity of the number 4. And definitely not number 2. So, yep. Which means, well, it's definitely not 2 times the displacement. It's a lot closer to 4 times the displacement, which is what conventional science would predict. Okay, so this is, I think, proof that kinetic energy is real. Of course, this is the substance. The substance is flour or floral foam, so I might as well try it with clay. But this is a really good material for measuring impacts. Anyway, so I think this is a good experiment.